As usual, you're looking for tasks to complete for U3L6 on under assignments or on the campus homepage in the weekly calendar. Today's date is December 1st. Happy December, everybody. We're going to start off with the usual breakout rooms chat. The question, I'll throw it in the chat just so you can all see it as well, is, here we go. If you could pick up a new skill in an instant, what would it be? You guys haven't answered this before, have you? No. And skill, I define very broadly. It could be a language, it could be cooking, it could be a sport, it could be whatever. So you can be specific or broad, doesn't matter to me. So think about that for about 20 seconds. Share your answer, and remember to say hi and check in with whoever you're with as well. We'll come back together in 2 minutes. Rooms are open. Everybody. All right, next on the docket was a formative assessment probe. Just like what we did in our previous lesson, I'm going to have you read through statements from, I think, 6 different people this time. They're debating a question. The question this time is, why does rain fall? You need to decide who you agree with and why. And again, this is graded for completeness, not correctness, right? So don't try to, I don't want you to like look things up or refer to notes because I want to get a snapshot of what your current understanding is. Like, what do you think right now? So go ahead and on the task to complete list, that's step number 2. Complete that short Canvas quiz. I'll give us 10 minutes to do it. I'm hoping it won't take 10 minutes to complete. We'll come back together once it looks like everybody's done. 10 minutes to work on why does rain fall. Go for it. So feeling good there. The trick here, again, why Lorna is, I think, her statement about water being, clouds being made of vapor that then condenses, that's a very common misunderstanding. You have to understand, as we emphasized in our previous class, that clouds are already liquid. It's little tiny liquid droplets that are condensed onto dust and ash and all the stuff in the air. And then when those glob together to get big enough, they become too heavy, that's when they fall. And that's when the clouds darken. So something we'll keep reviewing. Great. Any other questions or comments on the formative assessment probe? All right, homework was looking good. I'm seeing 9 responses to the cloud in a jar Flipgrid. So please make sure to email me your video if you couldn't get it to upload onto Flipgrid, or if you haven't done that yet, please do so as soon as you can. Let me know if you need help. The Ed puzzle, which was review of Hewitt chapter 26.8, all about water in the atmosphere, which we're going to continue to review a little bit today and build on. Again, about 12 or 13 of you have it done, so if you weren't able to complete that, please do so soon. Or there's also a Google form alternative if you can't get Ed puzzle to work. Any questions or comments on that classwork from our previous class? Wasn't technically homework, but if you didn't get it done, you just need to get it done on your own. All right, what's gonna happen now is we're gonna sort of take a little gear shift. We've been talking about water in the atmosphere, and in order to understand more about what's going on with weather and clouds and rain and precipitation, you need to understand some chemistry behind the states of matter and phase changes. So we're gonna kind of delve a little bit into kinetic theory and what's going on with the different states of matter. So I'm hoping some of this is review, but I want to get some details down. Just to get verbal confirmation, everyone's seeing a little graph temperature of tea in front of them?
Yes.
Yes.
All right, who is brave enough to tell me what is the joke that this graph is telling you about tea? I'll pick a victim if no one wants to volunteer.
It's too hot and then it's too cold.
Yes, if any of you are tea drinkers, it tends to be like boiling lava hot when you first make it. You're like, okay, I'm gonna let it rest. And then the next time you touch it, it's like below freezing. I mean, not really, but the idea is just that, yeah, there's a very small period of time when tea is actually the perfect temperature. Very good. So we got to talk a little bit about temperature. And in order to understand that, we have to talk about what's called kinetic energy. And again, I'm hoping this is review. Kinetic energy, remember, is the energy of motion. Anything that is moving has kinetic energy. This is different from potential energy, right? Potential energy is the energy of position, stored up energy. So for example, this bicyclist right here, This person, once they were sitting at the top of the hill, um, they had potential energy when they weren't moving. They were at the top of the hill, ready to go down. But now that this person is in motion, they have kinetic energy. Now, these are all big examples, but you can get down to a molecular level. Technically, if you have a glass of water sitting in front of you, that liquid is moving. It's made out of millions of little tiny H2O molecules, and they're all dancing and moving around each other. That is also kinetic energy. And that is what temperature measures. So when we say we're measuring temperature, when you're saying the average temperature outside is, what you're really saying is what's the average kinetic energy of the air molecules that are outside, right? So if you have a glass of water, if it's hot water, that means that all those little H2O molecules are moving around really, really fast. They have a lot of kinetic energy, very high average kinetic energy, high temperature. If it's very low movement, very low kinetic energy, then that would be a lower temperature. The tendency is that heat will always go from higher temperature to lower temperature, right? So hot things will always transfer their energy into colder things. And this is just by the virtue of movement, right? Heat is accelerated movement, right? The more molecules are moving, they're going to bang into each other and promote motion in other molecules. What gets a little weird, and this is something I want you to pay close attention to because I'm going to ask you a question about this, is what's going on when something is absorbing heat. If you have a reaction, right, we refer to these often as endothermic reactions. So if you think about like a cold pack is an endothermic reaction. It's absorbing heat. Whatever's inside of it is becoming warmer, right? It's gaining energy. But when you touch that thing, it's going to feel cold, which I know is counterintuitive because it's like, wait, it's absorbing heat, it's gaining energy, but it feels cold to the touch. And the reason for that is because when you touch this, it's removing heat from your finger. So that's why it feels cold to us, because it's literally sucking heat out of your own fingers. That's what gives you that cold feeling. Vice versa is also true. Anything that is releasing or transferring heat, so things that are giving off heat, they're losing energy, they're cooling down, they're actually going to feel warm to the touch, right? We refer to reactions like this as exothermic. You can get hot packs, right? If in cold places, those are exothermic reactions. It's when you touch it, it feels warm. The reason for that, again, even though it's losing energy, it's releasing energy, it's actually becoming less energetic. The reason it feels warm to the touch is because that energy is being released into your finger. So again, I know it's a little counterintuitive, but just something kind of to keep straight in your mind about how we perceive temperature, with our fingers and things like that. Okay, states of matter, I'm hoping are pretty straightforward. We're just going to briefly review solids, liquids, and gases, and I'm going to talk about kinetic energy and a couple other properties. There is a fourth state. Does anyone know what the fourth state is beyond gases?
Plasma?
Yep. Plasma is essentially a charged gas. We're not going to touch on that very much. So solids obviously have very low kinetic energy. Particles are technically vibrating in place. So here's what a solid would look like on a molecular level. You can see them kind of shaking in place right there. They will take any shape and maintain that. So, if you have a rock in a glass and you pour it onto a table, the rock is not going to change its shape, right? They're fixed. They have very strong attractive forces holding them in place, and they tend to be very, very compact. They're very close together, so much so that we say that solids are not compressible or cannot be compressed. What that means is you cannot shrink the volume. I could apply lots and lots of force to the outer edges of the solid. I would not be able to decrease its volume. And yes, a lot of you think you will wait, you can crush a rock. Yes, you can, but all you're doing is turning it into a powder. You're not actually shrinking the volume down, right? So it's impossible to shrink the volume of a solid. You can't compress it. Liquids are very similar to solids. I know it seems a little weird, but I want you to make that association in your mind right now, is to group solids and liquids together. They have a little bit more kinetic energy. The molecules are technically sliding past each other, as you can see in this diagram, but they're still very close together. They'll take the shape of whatever container they're in, as you know, right? If you have a glass of water poured on a table, it flattens out on the table as gravity is pulling the liquid downwards. They still have attractive forces between them, which is why you get things like droplets with solids, and that could be with liquids. It could be liquid water, it could be liquid mercury. You always see little droplets form because they are so attracted to each other. And like solids, they cannot be compressed. Now, technically, you could say the liquids are somewhat compressible, but for your understanding, I want you to associate them with solids. We cannot compress them, which means, again, if you were to apply a ton of pressure to this liquid, you would still not be able to dramatically change its volume, right? They're still very close together. Gases are unique. They're very different from solids and liquids. They have incredibly high kinetic energy. The molecules are moving very fast and erratically, bouncing around everywhere, lots of space between them. They take the shape of whatever container they're in, and if they're not in a container, then they spread out within the atmosphere. They have little to no attractive forces between them, which is, again, is why they often are expanding out. And they can be compressed. And this is what makes gases so interesting, is that you can capture a gas and you can exert force on it to shrink it or less force to expand it. That creates what's called pressure. We're going to learn a lot about that in a little bit. But again, it's just because you have all this space between the molecules, that's what makes them compressible. Okay, first poll question for you to answer is on the screen right now. Give this a go. And just a reminder, these are not graded. These are totally anonymous. So if you're not sure, just take your best guess. Meant to be kind of a quick survey. Okay, seeing 12 out of 13 responses. All right, I'm going to close it down. All right, here are the results. Interesting, we're very torn. Again, I know this is a confusing concept that I only just threw at you, but the statement was, in a reaction where heat is being lost or released, keyword there is released, a transition from high to low energy would feel, again, so if you have something, an object or reaction that is releasing energy, if you were to touch it, that energy is going into your finger, it would feel warm to the touch. So warm was correct. So more of you did get the correct answer. But again, I know it's weird to think, wait, it's losing energy. Wouldn't it be cold? No, again, the energy is being released outwards into your finger, and that's why it feels warm to the touch. Even though it's exothermic, it is indeed losing energy. All right. Here's a nice little summary table. So if you got a little lost there, if you want to kind of see it all in one thing, this is looking at all three of those main states of matter and everything that I just kind of summarized about each one. So this is nice to make comparisons. Here are the classic images that you see of how the molecules or particles of matter behave. And again, I just want to emphasize that solids and liquids are very similar to each other. Gases are completely different. We're going to spend a lot of time learning about gases in particular because they do a lot of interesting stuff. But again, think of solids and liquids as being generally low kinetic energy and gases much, much, much higher kinetic energy. So how do we transition between these, right? We have names and words that describe the change from solid to liquid, liquid to gas, and so on. I'm hoping you know a lot of these already. So help me out. What do you call it when a solid goes to a liquid?
Melting.
Good. The scientific phrase for that is actually called fusion. If you ever see the term heat of fusion, it means the heat of melting. What do you call it when you go from liquid to gas?
Evaporating.
Good. That's one example. Evaporation is one example. You could also have, does anyone know what you call it when you bring something like water to 100 degrees Celsius?
Boiling point.
Yep. So there's boiling, evaporation. All of those are transitions from liquid to gas. So the catch-all phrase for it is vaporization. That's why, again, these e-cigarettes that take a liquid and turn it into a gas that you inhale are called vaporizers, right? So vaporization is just the catch-all term for evaporation, boiling, all that stuff. All right, what's the opposite then? What do you call it when you go from gas to liquid?
Condensation.
Good. That's what happens on the side of a Coke can. A lot of people say, oh, my Coke can is sweating. It's not actually not what's happening, right? It's liquid water from the air. The air was a gas. It hit the side of the Coke can, which is much colder, and it condenses into liquid again. So it's coming from the air, not from the can itself. What do you call it when you go from liquid to solid?
Freezing.
And very good. And again, a more general term to use for that is solidification. You could also say that. Okay, tricky one. What do you call it when you skip the liquid state, when you jump straight from solid and go all the way to gas? Anyone know that?
Sublimation.
Very good. Yeah, sublimation. And the opposite of sublimation, it's like making a deposit at a bank, is called deposition. We'll kind of touch back on these because there's some cool examples. If anyone's ever played with dry ice before, which is frozen carbon dioxide, that will sublimate. It goes straight from ice to gas. So there's a lot of fun little experiments you can do. So great. Now, what's going on with kinetic energy? Obviously, as you go from solid to liquid to gas this way, you are increasing kinetic energy, right? You're taking molecules that were standing still or vibrating in place, and now they're a gas, they're very excited. So that's an increase in kinetic energy, which means you need heating to go that way. I should use red ink to draw that or something. So then obviously the reverse is a decrease in kinetic energy. You have to remove energy, right? Decrease the motion. And so that's the way we kind of summarize these. So heating will cause an increase in kinetic energy, more activity in the molecular level. That's what's going on with melting, vaporization, and sublimation. Those three transitions all involve an increase in motion on a molecular level, right? Cooling, which is the opposite, slows things down. That's what's going on with solidification, condensation, and deposition. Energy is being removed. Molecules are not moving as much. They're coming closer together, compacting, that sort of thing. So here's a nice little kind of summary slide showing you each of the transitions, the three states, and I like that they have the little kind of animation showing you the molecules. So again, it's hard to imagine exactly what's going on when they're static, but you'll be doing a little simulation later, which will more accurately show you what's going on with the molecules. Okay, second poll question is now on your screen. Give that a go. All right, I've seen 12 responses. Give it 5 more seconds. One more. All right. Here are the results. Good. Looks like we're feeling good about sublimation is indeed the phase change from solid directly to gas. It's called sublimation. All right. So far I've been very temperature focused, but what might surprise some of you is that pressure can also change states of matter. You can make something transition from solid to liquid or gas by applying pressure or changing the pressure, and sometimes even just keeping the temperature the same, which is kind of interesting. And so that's going to introduce us to what are called phase diagrams, which we're going to come back to a few times here. This is an example of phase diagram. As you can see, it's a graph. On the bottom, we've got temperature increasing, right? So you've got low temperature to high temperature. But on this, the y-axis, you have pressure, going from low pressure to high pressure. And so not surprisingly, things that have very low temperatures and very high pressures tend to be solid. When a substance is experiencing medium temperature and medium pressure, it tends to be liquid. And when something is experiencing very high temperatures but very low pressures, it tends to be a gas or vapor. And so this is just showing you the general temperature and pressure points, what state this substance would be in. And this example is water. So it's showing you where, under what pressures and temperatures would water be solid, liquid, or gas. And so what makes this interesting is that you have these border lines. These are the transitions. So I heard some of you referring to boiling point or melting point, that kind of thing. That's what those lines are showing you. It's the boiling point. So this would be the melting point or freezing point. This would be the boiling point or condensation point. But what I think is really fascinating is down here. See how everything merges together? That there is called the triple point. And it's called triple point. And we want to guess what technically can exist at the same time. At this point, at this pressure and temperature, right here and right here, water could be what, and what?
A solid, a liquid, and a gas.
Yep, all at once. And you would see freezing, condensing, boiling, melting, all happening at once. It looks really chaotic. I'll show you a video at the end of the slides showing you triple point, but it's kind of cool. Note also that the phase diagrams for different substances don't all look the same. So the one I was showing you was water, which has this very characteristic shape. Those are the border lines between the different states of matter. Here is the same diagram, but for carbon dioxide, and look at the difference in the shape there. Clearly, carbon dioxide wants to be a gas most of the time, right? That's how we experience it. if you want to see liquid carbon dioxide, you have to increase the pressure drastically, right? And if you want to see solid carbon dioxide, you have to really bring it to a low, low, low temperature. So just kind of interesting to see the different properties then about a substance right there on the phase diagram. Now, you can actually label the transitions as I was noting on a phase diagram. I'm not going to take time to fill in each of these, but again, just always remember that you've got temperature on the bottom, you've got pressure on the side, and then usually, again, you've got solid where it's high pressure, low temperature. Liquid is almost always in the middle, and gas is usually at the higher temperature, lower pressure end. And so each of those transitions, as I was mentioning, melting point and freezing point, is that borderline between solid and liquid. Vaporization point, boiling point, condensation point is the borderline between liquid and gas. And then you've got the same transitions here, directly between solid and liquid, and there's your triple point. Now, if we were on campus, we would do a pretty cool laboratory where you can find the triple point using dry ice. I'm going to see if I can adapt something to make a simpler version that you might be able to do at home. I want to just very briefly touch on the idea of specific heat. If this was a chemistry class, we'd do a whole unit on this. But right now, I just want to give you the definition. So specific heat is, it's a measure of energy. It's the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. It's all based on water. So we say that for water, it takes 1 calorie of energy to raise 1 gram of water by 1 degree Celsius in temperature. So really all this is showing you what heat capacity is referring to is how easy or how hard is it to heat something up, right? And so not surprisingly, things like liquid water, it actually takes a lot of energy. If any of you have cooked pasta before, you have to put a big bowl of water on top of a stove and wait a few minutes before it actually gets to that boiling point. Whereas think about the pot itself, right? Most pots are iron or silver, steel, something like that. The minute you put that on the stove, on a stovetop, it's a matter of seconds before that metal is too hot to touch. And so these all have what are very low specific heats. They heat up really, really quickly, right? Metals in particular are very good at absorbing energy very fast and being really, really hot. Liquid water, and I shouldn't say very good, right? That they have a low heat capacity, right? That they heat up really quickly. Liquid water is what's really good at absorbing lots of energy and not changing its temperature, right? So they have what's called a high specific heat. So high specific heat means it can absorb energy and not change its temperature, right? It takes a lot of energy to actually warm up something like liquid water or ethanol. Whereas like metals heat up really, really fast. And so this kind of applies to nature, right? If you think about the oceans on the surface of our planet, that's a lot of water that's absorbing solar radiation from the sun. And so coastal regions in places like California, as you can see here, tend to have much cooler temperatures because ocean water has a high specific heat, meaning it absorbs a lot of the warmth coming from solar radiation. It also cools down the air that is above the ocean water. And so check out the average temperatures in coastal cities like San Francisco, Santa Barbara. They are way cooler than somewhere like Sacramento or Barstow, which are more inland, not as close to the ocean technically, and therefore experiencing much higher temperatures. So anyway, I just think it's kind of cool to think of the oceans as Earth's air conditioner because of that high heat capacity for water. And again, something we'll keep exploring a little bit with some activities. Last poll question for you. Give that a go. Okay, see 12 responses. All right, here we go. So yes, very good. Once again, a metal spoon left in the sun will heat up very quickly. It can also be too hot to the touch sometimes. And some of you might experience this with your electrical devices. If you ever left like your iPad, your iPhone out in the sun for a little too long, it heats up super quickly. And that's because metals have a very low specific heat, right? If they had high specific heat, they wouldn't heat up very quickly. All right, any questions or comments on that material? You'll be reading a lot about that in Hewitt tonight as well. Okay, then enough from me. I'm going to throw you into breakout rooms with a partner, and I'm going to have you work through a little Canvas quiz I put together that's based on a PhET simulation. The PhET is called states of matter, the basics. You're going to start off with states and then move on to phase changes. But this is really cool because it actually shows you what's going on a molecular level. It's all animated. You can see a gas. They're all bouncing around. And you can change with settings and things like that. I have instructions in the quiz itself. So on the tasks to complete list, we're on step number 5 right there. Just click on that link there, states of matter PhET simulation. It'll take you to the actual quiz and just follow the instructions and answer the questions. In breakout rooms, you should assign one person as the reader who will read through the instructions and read the questions out loud so that the partner can follow along. Timer, your job is to keep an eye on the time announcement that I will blast out to each, to the groups, and make sure that you have both answered the question before you move on. So I shouldn't see like one person finishing, the other person still working. Make sure you stick with each other to get this done. Questions on that? Okay. Again, I'll make a time announcement, but we'll probably go for, up until there's about 2 minutes left in class. So we're looking at about 15 minutes to get through this. And if you don't finish it, then it'll just move over to homework. So I would definitely get as much done as you can right now. Breakout rooms are open. Go for it. All right, welcome back, everybody. Hope that was somewhat helpful. It sounds like, and from what I'm seeing online, looks like most of you still have a little bit to finish up. So that will just roll into homework. You don't have to keep working with your partners. You can just finish it on your own. But I hope that animation was helpful to show you what's actually going on with the molecules and the way they bounce around. As you can see, it's not always that clean in terms of like what's a gas, what's a liquid. But I find it helpful to play around with that. Was everyone figuring out the whole like click and drag up? You had to like hold the flame or hold the ice up. Other groups had a hard time with that. So just make sure you're clicking and holding that up to change the temperature. Any other questions or anything you got stuck on the quiz? All right, you'll be reviewing it as homework. So homework is actually a change. You're gonna be, you're still doing reading, submitting notes, but we're not in chapter 26 anymore. So you're gonna be reading parts of chapter 11, 11.2 and 11.3 in Hewitt. But then the usual deal, submit a photo of your notes, and there is a reading quiz you have up to 10 attempts on. And please just make sure you finish that quiz using the PhET simulation. Questions on that? All right, kiddos, that is it for me. Thank you very much. Have a good day.
Thank you.
Yeah.
You.
Thank you.